Welcome to the third episode of the Kern Competence Podcast, a podcast by Kern about all things precision. Today I am once again joined by my co-host and our CEO, Simon. Welcome, Simon.
Thank you very much, Marvin, and welcome to you.
It's quite funny. It was about a year ago that we started recording the first episodes. And, well, we just published the first one. Was pretty good reception there, I think. And yesterday I listened to the second episode before today we are recording the third one. And what is really funny is the first 5 minutes of the second episode, we are talking about how hot it is in Germany. The weather is extreme and there is like a heat wave. And this morning, I'm not sure, did you have snow on your car?
I did.
Yes.
And we changed to summer tires. I don't know if everybody knows what winter and summer tires are, but actually we changed tires in the season. So we changed to summer tires and right there it started to snow again, as every year.
I changed to summer tires 2 weeks ago on Easter, just before going home over Easter to my parents. And I drove via Austria over the Fernpass. And with brand new summer tires on that Thursday, it was actually snowing. And I was like, why did you do that, Marvin? So yeah, it must be this way if you live in the Alps and you change to summer tires. This is just the way of the universe showing you.
Yeah.
Exactly. Okay, today we're going to talk a bit about our machine. Everybody knows the machine, the Micro HD. And you know that machine from videos, you know it from us talking about it. And we always tell people it's supposed to be really precise and some clever engineering. So let's talk about what makes the HD so precise, about the technology inside.
Very good point. Yeah. So if you look at the Micro HD and actually the technology step we took at that time, most importantly is the material we choose and the whole technology by guiding, respectively, the whole frictionless system, the three-axis move. And there's the first question to you, Marvin. What do you think is the most important attributes for a three-axis system?
Yeah, I think it's mostly the guideway system. If you look at traditional machines, you often have roller-bearing guideways. And roller-bearing guideways, they kind of work like a linear ball bearing. So you got small metal balls. They are arranged along a steel frame, and then you have some sort of cage which brings the balls back to their position. And while that system has been proven a lot, there are some shortcomings to this one. First off, when one of the balls enters the carriage, you can actually detect a lift because, well, there's a new component entering the carriage and you can detect that lift. It's in the 10th of microns. But for example, if you're a diamond finishing, this is something which can be visible on your part. But moreover, you got certain friction attributes. On the HD, we choose a different approach. We took a hydrostatic guideway system. Now, Simon, you're also a technical expert in this company. No, you definitely are. You know our product much better than most people. If you look at the properties of a guideway system that you want in a machine, what are you looking out for? What do you tell customers that make our machine special?
So I would say it all comes down to three main attributes. Besides that, there are many others, effects and side effects that might play a role in the different kind of processes customers ask us or challenges customers address us with. But I think most importantly, it's the three. It's friction, stiffness, and dampening. And perhaps we come to the 3 points separately. So, of course, what you want to have, what you already said before, is low friction. So low friction is something we're looking at since we have the Pyramid Nano that has been launched to the market in 2005, developed from the 2000s on. So actually a machine that is there for nearly 25 years now. And low friction, the best way that we found is, of course, the hydrostatics, but and to avoid stick slip effects. So a stick slip effect, what we see, I always try to explain it if your car breaks down, so especially the younger ones might know. So in my 20s, I know exactly what that was because of the fact that my car always broke down, is if you try to push it, so the most of the energy you need at the very beginning. So you need to push really hard for it to start rolling. But once it rolls, it actually is a lot easier. And that's the so-called stick-slip effect. That's what we also see in every kind of access system. And this is something where you need more energy at the beginning. It's like, how would you explain the wave of force you have to apply? It's like...
I mean, the technical reason behind this is on every material pairing, you get a certain coefficient of friction. And that coefficient of friction exists in two versions. The first one is the gliding one, so when it's slipping, and the second one is the sticking one. And I think a good metaphor for this is looking at Velcro. If you have Velcro and the Velcro is completely connected, it's super hard to separate it. But if you take the Velcro and you do not have both parts put together and you slide them along really quickly, they kind of don't really connect and you still get some slippage there. And on a microscopic level, every material has the same. You have the dangling bonds from the atoms, you have the morphology of the surface, so every pairing has more resistance while it's resting to get it moving, and less resistance while it's slipping. And that effect is called stick and slip. And in technical control, this is quite difficult to handle because you know how much energy your motor needs while moving in axis. And you can also design your control loop to be perfectly fine while moving, but then the machine is stopping, for example, to turn the other way, and then you got more resistance. And this is something you can see on very cheap CNC machines, and on good CNC machine, it's still there, and it's something you can see on the surface, especially if you want to get spectacular surfaces.
Yeah, and exactly this effect is what we try to avoid with the hydrostatic system, especially also with the microgap hydrostatic and the integrated linear motors. And the next thing is
wait. Now you threw in something. You said microgap hydrostatics. And this is kind of where it gets interesting at the Kern company. If you look at the market standard for hydrostatics, it's usually quite the thick film. Industry standard is something around 50 microns. And if you look into our brochure for the HD, it says microgap hydrostatics. And then people are like, oh, well, it's Kern Microtechnik, probably something to do with that. I think we don't really tell people the exact value of our microgap height, but it's in the single-digit micrometer range.
Yeah, that's what we say. It's below 10 microns.
Exactly. And it's a curious decision to reduce that height. As you well know, we do our own axis manufacturing, and with a very small gap height, you need to produce more precise axis parts. Because, well, if your film height is below 10 microns and your axis flatness is larger than 10 microns, it's probably not going to work out, right?
Yeah, true thing. And this is pretty funny so we don't market that. I would love to market it, but actually... the technical team also around Sebastian is always a little bit hesitant about that. And also right now we're trying to find new ways to produce even higher flatness of the axis by using different kind of production methods. But for the last couple of years, we actually hand lab the axis. So we have respectively 3 guys hand lapping each and every single axis, which takes roughly a week. So this is quite an intense and labor-intense
process.
Yeah. And actually one of the most, I should say, expensive parts in production. And when we are short on things for producing micro HD, it's usually always the axis. Because of the fact that we have a certain number we want to reach, which is in the very low single-digit micron range in terms of flatness, respectively deviation there, and this takes some time. And for example, Mehmet is doing that since many years. He is very experienced, and he has, especially, how do you call that, the resilience is the wrong word.
The patience.
Yeah, the patience. Thank you very much. He has the patience to do that in the best possible way. And so I think after 2.5 days, I would like to throw this thing into the next corner. But
I think you and I are very similar there.
yeah, but Mehmet's not. So he's the right guy to do that. And it's actually pretty cool to see how we do that.
Yeah. And I mean, we are not doing this because the name fits well with our company name. By having a reduced gap height, another property increases. So Simon, which property increases by reducing?
Super important, high stiffness.
Yes, stiffness. Why would you want to have high stiffness on your machine tool?
Mainly because of the fact, and we're trying to combine two things that don't go together very well usually. This is high precision and very high dynamics. And high stiffness is mandatory for having a very dynamic behavior of the X system in general. So the higher the stiffness, the faster we can go, and we can control the dynamic effects of the machine. So therefore, this is very important. If you compare that, for example, to the Pyramid Nano, which is not in the range of microgap hydrostatics, but in a range of 25 microns, you see a big difference.
Yes. And I mean, this is something we've been known for in the past couple of years, that our machines are really precise at a high productivity. If you, for example, not only the Pyramid Nano, but if you compare it to a diamond lathe is super precise. Often they also have hydrostatic guideways, but they are not very stiff. And if you ever move or jog a diamond lathe at rapid feed rates, you can actually see it deflect when it stops. So those machines are meant to be operated really, really slowly, which in turning is fine because your feed rates are very slow, especially in diamond turning. But our customers kind of want to produce parts and earn money. And well, for that, you need some productivity. And it's always surprising, especially if you do it as a customer demo, if, for example, you just want to hit some hole diameter and you interpolate a hole at like normal finishing feed rates, and it's like a meter per minute feed rate, and you hit the tolerance spot on. And then you turn up the feed rate 5 times to 5,000 meters, which on most machines is like the roughing feed rate, and you still hit the same tolerance because the machine is not deflecting in any way. So high stiffness, especially the dynamic stiffness, which most manufacturers don't even look at, is super important. And the stiffness increases proportionally with reducing the micro gap height. So by having a 5 times lower gap height compared to the Pyramid Nano, the dynamic stiffness is actually 5 times higher, which is amazing for our product. Now, if you have a machine which is too stiff, imagine it would just be like a diamond, a single diamond, stiffest possible machine. You would run into another problem which the hydrostatics avoid. So the third property we are looking for in an X system
is a dampening effect. So high dampening. So if we go, for example, as you mentioned, the roughing circles, then you don't want to have chattering and things like that. So no dynamic effects also on your workpiece, respectively. Dynamics having an effect on surface quality, for example.
Yes. Dampening is also something, especially if you want to have really smooth surfaces, if you want to have high quality, dampening is really important. And the dampening property in hydrostatics, it is basically the viscosity of your fluid divided by the gap height to the power of 3. So you can see that with reducing the gap height, our dampening is actually increasing. Now, there's the viscosity in that formula. And also, if you look at the friction basically is proportional to the viscosity multiplied by the inverse of the gap height. So friction actually increases with reducing the gap height. And the very clever approach our head of development, Matthias Fritz, took there was to design this system in a friction-neutral approach. So by reducing the viscosity of the oil used in the hydrostatics, you arrive at the same friction coefficient compared to a larger gap height. And obviously, by reducing the viscosity, all the other properties change as well. And the nice thing here is, if you just look at the formulas I mentioned, by keeping it friction neutral, you have a linear increase in stiffness because the friction doesn't appear in that formula. And you increase the dampening with the second power, your stiffness stays the same, and you get also a decrease in the flow rate. Now, why would you care about the flow rate? Well, nowadays, politics are sitting in our neck and rising energy prices, and this is actually something spectacular on the HD, that we consume, especially because of that micro gap height, we consume very, very little power for the hydrostatic system.
True thing, very important at that point, and becoming more and more important. The more customers we visit, we hear exactly that energy efficiency topic very often. And what we have to say is, because I don't want to claim that the Micro HD is a super low energy consuming machine, but for what we are doing in the range, what the abilities of the machine are, yes, we are there. So for the parts, for the dynamics, for the precision you have, for everything you need around, actually make that machine temperature stable, yes, that's a very important effect to optimize also in energy efficiency the machine as good as we can.
Yeah. And talking about energy efficiency, this is something, and I don't think we ever showed you those measurements, but we recorded the axis current on the Micro Vario, so roller bearings, and on the Micro HD at maximum feed rate. And just looked at like how much power do you need to drive the axis system. And they are pretty much the same weight. They are both made from aluminum. They both have the same spindle in it, so it's a pretty good comparison. And what is funny is that you actually use significantly less power on the HD at maximum feed rate compared to the Vario. But the HD has twice the maximum feed rate. Mm-hmm. So that's I think really impressive to show what low friction brings. And you always have to remember that friction also creates heat in the system. So I would say this is another advantage of having really low friction. Not only are you saving on power, you're generating less heat in your machining system, which makes the whole machine more precise.
Yeah. And there's also one thing that comes with low friction is low wear. And enemy number one of a precise machine tool is of course temperature, but the second is wear over time. So if you want to have a machine that is precise also after 5, 10, 15, 20 years, then this is where you want to go. Sorry.
Good. I mean, usually when you look at machines that have been out there for quite some time, I think last year we got the first ever Micro back from the customer in Northern Europe for a complete overhaul. And I mean, you can see things like the paint is wearing down. And obviously they had all of the roller bearings, all of the servo drives, all of the ball screws replaced. And then you look at the Pyramid Nanos out there. And what are they replacing on the 25-year-old Pyramid Nanos? Well, they are replacing the spindle. They are maybe replacing the bellow covers. I haven't heard of a Pyramid Nano having its guideway system replaced.
Yeah, true thing. So the only difference I would say in the Pyramid Nano is that in a crash, and I think we talked about that in one of our previous episodes, in a crash you actually can have the physical touch of the axis, respectively the guiding systems in a Pyramid Nano, and of course you create instantly a lot of wear. That's the same thing for a Micro Vario, and the machine you talked about is one of the very first machines that have ever been sold to customers. And I've been in Sweden last week, and we visited this customer. And if you see, this is a machine that is now close to 15 years old, Micro MF11, and they are making absolutely outstanding parts on this machine. still, but now even more than before because of the fact that also, of course, we upgraded what was possible at that time. They're super happy with the machine, which is a pity because we wanted to convince them to buy a micro HD, which we will not stop until they finally have one. But they're super happy with this old machine, which is also coming back also to things like sustainability. Is something that gives us kind of pride to be able to have machines out there 15 years old still being in the top level of precision, producing parts for highest demand application. And but coming back to the Pyramid Nano, this is what we will see in the micro HD, since there is really no physical touch of the metal components in the 3X system possible. We will see that even in 20 years from now, we will not have any kind of wear. Of course, you have components like sensors, like electronics in a machine that will wear over time or will be less efficient or break down. But the core parts, the access system, which of course would be the most expensive ones to replace, this is not going to happen. I'm 100% sure about that. And as you said, we see that in the Pyramid Nano too. So if you crash a machine, yes, but even that will not happen in the micro HD. But if the machine is running smoothly over time, we will not have any issues with the access at all.
I think that's also a very convincing argument for an HD. I mean, I usually don't look at the cost of ownership because, well, it's your company. You give me the machine, but you probably look at the cost of ownership for this, and this is something that comes up with customers. And I know our initial price for the machine is not a low number. It's not super expensive for what it is, but it isn't a cheap machine. It's made in Germany, it's a high-quality machine, it's a world-leading technology product. But if you then look after owning the machine, and I mean there's a massive amount of money you can make with the machine, but just like the cost of ownership, the repairs, the maintenance you have to put into the HD, I think this is really low.
Yeah, dramatically. So what we see today is that we will have some challenges in the future also concerning the service team because of the fact that we have totally different kind of service interventions for micro HD than for the other machines we once built or still building today. Maintenance is an important point. So what we do today more than in the past is having certain schedules once a year to look at the machine. Not everybody does that. I would say that the machine is not going to break down because of that, but what you want to do is especially Americans know that, yes, you want to protect your investment, you want to ensure that everything is running smoothly and you don't want to have any kind of breakdowns. And by having these interventions, you can avoid those because we do a lot of measurements, especially around the components that what I mentioned before. But the system itself, well maintained, will run forever, and there's no bolt screws that needs to be changed. There's nothing. So actually, when we hear customers asking us for spare part lists, it's filters and oils, and that's it.
Yeah, mostly.
Yeah.
So yeah, I think that's very convincing, and you can see that a lot of the time when customers come into the company and they are interested in a Vario, and then they see the company, and obviously we show them the HD, you can see that there's a certain longing after having the HD, especially because of this one. Now, one part both machines share is the material the axes are made from.
True thing. Alumina.
Yes. It's I would say, most of the time, this gives you raised eyebrows by your customers because they are like, excuse me, why do you make your machine from such a soft and weak metal? But, well, we don't do things without reason at Kern. So there are a couple of factors for aluminum which really shine in the use of a machine tool.
Yeah. Before I go to that, so actually the whole thing about choosing this kind of material, and I guess we will dig a little bit deeper into that because there's some super important but also interesting topic. The company Kern, what we stand for actually is if we see there's a certain kind of progress or something is happening that is not in our control or not completely in our control, we're not trying to push it away. We're not trying to ignore it or to fade it out or try to make it as small as possible. But what we try to do is really work on it. This is true for many, many other topics that are left and right of the machine, but also internally. And I think the choice of material in the micro Vario and the micro HD is the representation for that point, because we're not trying to take thermal effects and try to minimize them with sheer mass or trying to fade them out through using steel, for example. But we try to work with it, and therefore you want to have a material that is extremely reactive versus, what would be the right word for that? The opposite of extremely reactive.
Slow.
Yeah, slow and lazy, or just a development that happens often uncontrollably, but over a long period of time in the machine. And when we look at many processes we are doing today, long-term stability on a micron, sub-micron level, this is what we're dealing with today. And with steel access, this is something that we couldn't achieve.
Yeah.
And of course, there are two things that come with alumina. This is
Before we get into the two things of alumina, I think I have to make a small intersection here, because you spoke about reactiveness and that you can't hide anything in this company. And I think this is a little bit of company gossip that's quite interesting to our listeners, is both you and Sebastian Guggenmoos are massively available for our employees here. And you know this very well. If the application department discovers any flaw inside the machine, there is no chain of reporting. It's the application technician or me standing in your office and complaining the machine is so bad.
Yelling
At you, and you have to fix it now because we can't work like this. So I think hiding something in this company doesn't exist in the company culture, because you can just go to the CEO and complain about how bad the machine is. And it isn't, but in the moment it feels really good to not go to your boss or go to the head of development, but to go to the CEO and complain how bad the machine is.
Yeah, which is super important. And of course, I have to say, this stresses you out dramatically. And you also know, for example, with our sales guys, and I say, if you look at all the sales guys, everyone has a background in applications or is an engineer or something like that. We don't have real salespeople like others have that are in the field for 25 years or something like that. They usually know exactly what they're talking about. They were in front of machines for many years, and they are super sensitive for things like that too. So when somebody comes in here and starts complaining about this and that, this is always also a very emotional thing, and you have this immediate sense of urgency to get rid of it. And it's exactly as you said, this is super important. We cannot be average, cannot be average. We need
this is not acceptable in the company.
And we wouldn't survive on the market if it would be like that. So actually, therefore, it's very important also for me to visit customers from time to time. And you don't only always hear just super good feedback. I have to be honest on that too. So we also have one or the other problems here and there, which we have to work on, and that's what we do. Therefore, both of us are traveling often together to hear that, see it, and make things better. But most importantly is that you get also the positive feedback for the things we've done and see, okay, this machine is different, and therefore this feedback is extremely important. And once we can never reach the point where people stop talking about those things, stop addressing those things. If we come to that point, we say, oh, you cannot bother him with that, we will have a problem. So therefore, important point I want to emphasize and motivate everyone to do that.
Yeah. Okay, so with getting back to the subject, we talk about the material for the access. Now, the usual approach is when you design, for example, a machine, any machine, that you look at material properties. And there's material properties like density, there's material properties like stiffness, maybe the Young's modulus, and often people go through the list and then they select one or two properties of these and they try to find the optimum material for that. And if you take that industry standard approach, you will probably arrive at either a cast iron or a steel frame. Now, we choose aluminum. And there's two factors that made us consider that material.
Those two factors are the specific beam stiffness. That's the first thing. And the second is the thermal stability.
Yes. Specific beam stiffness. This is quite interesting. Actually, both are quite interesting because they are compound values. So if you look at material properties, and I mentioned stiffness. We earlier spoke about how important stiffness is. Well, there is no exact value, no material property for stiffness. But there is one value, which is called the Young's modulus. Funnily enough, in German, it's the E-Modul, elasticity modulus. And this basically is the material property for resistance against elastic deformation. Now, the difference between elastic deformation and plastic deformation is the elastic one bounces back. So, for example, if you have a very long piece of material and you hold it straight out, it will kind of bend down. And the resistance against this is basically, well, it's also the area inside that beam, but it's mostly the Young's modulus. And the specific beam stiffness is actually the square root of the Young's density, of the Young's modulus, divided by the density of the material. And this is where aluminum starts to shine. Because if you look at the Young's modulus of aluminum, it's not very high. The one of steel is much higher. I think aluminum is around 70 megapascals and steel is around 210. So you would be like, hey, this is much better. And this is, funnily enough, completely independent of the heat treatment of the material. So like every steel is around 200 because it's mostly a property of the atomic bonds and not so much of the crystal structure. But if you bring the density in, well, steel is much heavier. And this specific beam stiffness, it's exactly the metaphor I mentioned earlier. It's you have a long beam of material and you look at how does it behave against gravity or load. And some values I can give you for that one because, well, you can calculate this compound value for material. And for cast iron, the value is actually 58.1. For steel, it's 58.4. And for aluminum, it's nearly twice that at 98. So if you want to build a machine which is light, but also stiff, aluminum is a much better choice than steel or cast iron.
True thing. And there's one thing I think we also mentioned before. If we would build the 3x system of the micro HD out of steel, it would be close to a ton of weight.
And at the moment it is?
Roughly 360 kilograms. And thinking about 2g acceleration and 60 meters per minute, you don't want to move a ton when you can move only 360 kilos. So from a dynamics, the machine is able to perform. Of course, aluminum gives a lot of advantage versus the steel version.
Something I also sometimes tell to customers which are less technically inclined is just look at a sports car. The frame of a sports car is not made from steel, it's made from aluminum. If you have a nice Porsche, it's going to have an aluminum frame and not a steel frame. And there is a reason behind it, because your sports car kind of wants to have the same properties as our machine. You want it to be relatively stiff because, well, you have a lot of power in it. It needs to handle well. But also you want it to be light because, well, cornering is all about weight.
Absolutely. So, and besides that, as you say, also the thermal stability that we see coming through the aluminum or alumina for us is very beneficial. And we can talk about that a little bit. And it comes back to what I said before. If you don't want to hide things, fade things over time, you want a material that is very reactive to the things that are happening. Because if it's very reactive, you can counterbalance, you can manage, you can handle it.
Yes, and you earlier mentioned another compound value, which is the thermal stability. Usually, when you're designing a machine, you might, with your material choice, you might look at the coefficient of thermal expansion. So that value in a material is basically the property if you heat 1 meter of that material by 1 degree Celsius or Kelvin, not Fahrenheit, how much is it gonna elongate? And if you have a bar of aluminum 1 meter long and you heat it just a single degree, it's gonna elongate by 24 microns, which is absurdly horrible if you consider we are making a precision machine, promising customers if they are really good, they can split a micron. We have a meter long z-axis and 1 degree is 24 microns.
Actually, that is what so Sebastian and I, every time we get new apprentices once a year in September, we invite them with their parents. And that is one of the first things we explain about a micron and building a machine that is able to perform micron precision in 5 axes. And this is exactly what we have. It's in Sebastian's office. We have a small bar of aluminium, which is a meter long, and that's what we explain. So you want to hit the micron, but actually if you heat it up by 1 degree, you already lost 24 microns. So that comes back to our temperature management system and how precise also that needs to be.
Yes, because that compound value of thermal stability is basically your temperature conductivity divided by your coefficient of thermal expansion. And your temperature conductivity, that is the material property that defines how well can you put heat into a material or remove heat from the material. So how well can you control the temperature? And if you look at that compound value, this basically gives you a ratio. And if that ratio is below 1, it means your material is not very easy to control. But if that ratio is above 1, this means you can control the elongation by controlling the temperature very nicely. Both steel and cast iron are actually far below 1 on that ratio, and aluminum is nearly at a ratio of 3. So it's nearly 3 times, it's actually probably is 3 times better to control the temperature of that material. Now, you mentioned that before, you need a very precise temperature control loop. But if you manage to get something like that working, you're left with a machine that is stable at every point. So no matter what load you have on the machine, it has the same precision. Something I often tell customers, it's actually car industry part we did a couple of years ago. It's like a compressor scroll for controlling the temperature management in battery electric vehicles. And it used to be a very cheap part because it's just like a cast aluminum part. And nowadays it's a milled part. And in that demonstration, in that customer workshop, we milled it from cast iron. Full slotting with quite the large end mill, and was like 120-person spindle load for little above 1 minute, just the maximum the machine could withstand there. And then we take a sister tool, and without doing any cool down cycle or anything, in the next minute we finished the form to way better than 5 microns form accuracy. And I think on any other machine on the planet, if you generate that much heat, like full roughing power, every operator would do like a cool down cycle. Just be like, hey, let's give the machine a short moment to equalize. And on the HD, we didn't do that. We just went like, no break. Just like next tool in, spindle on, let's go.
And that's what you need if you want to do more than 1, 2, 3, 5 parts, but you want to run 24/7. And actually, this part is on Instagram. I think we have a video on that, how we did it at that time. And that's also an interesting development we see today, that things that usually Kern wasn't made up for, or let's put it like that, considered at all, because it was all about price and getting the cheapest cost per part. Today it's about efficiency, getting less weight, smaller air gaps, and the smaller the gap, the higher the efficiency. And suddenly a part that wasn't allowed to cost more than €4 is allowed to cost €40 because it does make us so much better, or it performs so much better in the car, in the system. So we see those projects coming up that usually said, no, we don't do scroll wheels for automotive. But those days we do.
I mean, usually I would say we don't do a lot for automotive because most of the parts they need don't really fit on our machine. There's always new technology coming in, and then sometimes they want more precision. With those scroll compressors, it's all about the gap tolerance, and the closer you can get the gap tolerance, the more efficient they are, and this can be dramatic increases in efficiency. And for the car industry to switch to a part which costs 10 times more, there needs to be a significant difference there. Yeah, our temperature control is quite advanced, and Matthias once told me that we have like 5 principles for the temperature control in the machine. The first one is that we try to avoid heat. So if you look at the linear motors of the HD, they are massively oversized. I think you could easily throw around a machine 4 or 5 times the size. Now, operating an electric motor at very, very low load is not really that efficient in terms of energy consumption, but you are left with less ohmic losses. Because you have to imagine you are inducing a current in the motor, and well, that current is going to generate some heat. And if your motor is massively oversized, efficiency is not really high, so you lose a little bit more power, but you're generating less heat.
I think what Matthias once told me is that the higher you come to the maximum power output of a motor, the heat it generates is exponentially raising through this process. So the lower the load at that point, of course, also the lower the thermal effect you create with that motor.
And with the HD, obviously our linear motors are cooled, but we also do something very cool to the non-moving part, to the stator of the motor, where you just have the magnets. If you look at the axis system there, you can see, and I mean, they are screwed to the aluminum axis, and some heat is obviously induced in them as well. And now we're controlling the temperature of the aluminum. The axes are deep hole bored. There's coolant circulating through these, but we are also cooling that second part of the linear motor. So there is some coolant tubes directly below the stator, and we are cooling that one as well.
The primary and the secondary part is what we also temperature manage, which I don't know, but I think not a lot of others do.
I don't think either. Yeah. So the first one is like avoiding generating heat. The second principle is kind of like removing that heat immediately. On the Vario, we also have an approach for that one. The Vario is ball screw driven, and we have some servo drives. And if you look at the mounting bracket on the Vario, it is also water cooled because we don't want the temperature to bleed into the system. Now, the third principle is obviously controlling the temperature. We spoke about that a lot. We have a very advanced cooling system inside the machine. We are circulating coolant through the axis. What is the usual number we tell customers? How many liters per minute?
So in a micro HD, it's up to 200 liters a minute. So it's in Germany, 1.5 bathtubs.
I guess in America, it's like a third of a bathtub.
No, I think so. If you go to a Hilton Garden Inn or something like that, bathtub's pretty small, so I would say it's more than 3. But that's a point. So just to visualize how long it takes to fill a bathtub, you see how much water runs through that machine. With a micro Vario, it's 50 to 60 liters, so it's a lot less.
Yeah, I mean, this is also where you can really see the difference between the two machines, because often people forget that the Vario is an exceptional machine. But then if you look at different load states, if you look at difficult environmental situations, so for example, if you don't have a very high quality air conditioning system for your machine hall, the HD still shines. Mm-hmm. This is something where with a Vario you might have a little bit more troubles.
So we are very cautious with claiming that in brochures or something like that. But that's what we know today. Many of our customers, of course, it always also depends on what you're doing. So if you really try to split the micron, of course, the outside temperature or the environment plays a big role. But I would say for general, very high precision parts done productively, the micro HD can take a lot of change from the outside, which you will not see on the part, especially if you're using flood coolant and you cut out the workpiece also, and of course the tools. That might have a little different temperature going into the machine, but if there's flood coolant, the machine will be extremely stable also in changing environment over day, morning, noon, afternoon, evening, night. This is what we see very often, and thinking about for the next brochure we do to actually have a bigger part on that, to just show to our customers what to expect, because in 99% of the time we see people are very surprised how stable it really is.
Yes. And this is probably also because of the fourth principle. So after we have avoided heat and we have removed heat and we have controlled the temperature, the design of our machine, if you look at, and there are some pictures on Instagram from us where you can see the machine without a cover. If you look at the parts, you can actually see they are not like symmetric as in other machines, in the sense of, well, they don't appear symmetric. And this is because our development is actually doing FEM simulation on these parts to make them thermally symmetric. So we know where the heat sources are, we know how it pleats into the access system, and then the design kind of adds a little bit more material there to have a higher heat conductivity at that point and removes it at another point, so that if something is expanding, and I mean, obviously the spindle, you can't really control the temperature of the spindle that precise, there's just too much heat to remove it, but that the influence of this is reduced, that your expansion is symmetrically in all directions and not bending the machine in any which way.
Which would never be possible with, for example, having steel axis.
Yes. And the fifth principle is actually the digital component. So after we've taken every care to build the best possible machines in terms of thermal stability, for example, on the spindle, you have some elongation. And most people are actually quite surprised when they see for the first time what a very high quality Swiss high-speed spindle, what elongation it has. And our standard spindle, which is like the HSK 40 spindle, 42,000 RPM, from 0 to max RPM, you can actually see up to 100 microns elongation. Now, once again, we try to split the micron there. The industry standard approach is having a capacitive sensor at the spindle nose. Then you have a bar of material going all the way to the end of the spindle from something that doesn't really have a coefficient of thermal expansion. So, for example, Covar or Invar. And then you're basically, with that capacitive sensor, you're recording the spindle elongation, and the amount of elongation is compensated by retracting the z-axis. This is how we used to do it. Can you explain to our listeners how we are doing it nowadays?
Yes. So what you mentioned before, the 4 points, with all of that effort, with cooling, with the right material, with the right design and everything, we're not trying to, or what we achieve is not, there's no thermal activity anymore. But what we achieve is, it's always the same. So the machine is reproducing very, very nicely. So all that efforts go into that. So we want to know what happens. And then we once came to that point, and it's many years ago. So a lot of the efforts that we do here internally, also with our R&D department, if you count the heads that are just taking care of that specific part, that's a big amount. So what we're trying to do afterwards is making the machine very reproducible and stable over time, and then we add a real-time calibration in comparison to the sensors. So if the sensor detects an expansion, it's already too late. It already happened. So your tool center point moved down by half a micron, or whatsoever. In many applications, you will see that. And we also saw that if you have a sensor on your spindle nose. What we do today is we measure the machine in many, many ways over a longer period of time. We take an individual fingerprint, and still this This real-time calibration is not the same for every single machine, but every single machine has in this, let's say, nanometer range, its very own kind of pattern that we learn back to the machine. And we do a real-time calibration, meaning we don't have to measure to compensate, but the machine knows before what's going to happen. And we only measure to ensure that what we've done is right. And that's the big difference. So the tool center point, and you will see that in many, many tests we've done over the last couple of years, not only in the micro HD, but also in the micro Vario, for example, you'll see the tool center point will not move. This gives this outstanding stability of the machine and a lot of intelligence going back into the machine that once was standing in front of the control panel. So what you still need to have with a Pyramid Nano today. So if you want to work on a Pyramid Nano in that range you do on a micro HD, you need to know a lot. And this machine is more like a, should I say, like its own character, like a life form. You know, it reacts differently and reacts to the influences coming from the outside. And the micro HD will just take away the biggest bunch, 95% of that. And you can really focus on the process, which is a big step forward for us and what we will continue to work on the next years and hopefully decades.
Yeah. I mean, that model, so it's a mathematical model that is compensating the spindle elongation, and it is fed by data from every individual machine. And what I think is nice about this model is that even if you go to a higher temperature controlled spindle, so we also offer a compact shaft cooled spindle where the spindle shaft itself is cooled. On that model, it's not like it's superfluous. It's still needed, and it improves that performance even more. So on our normal spindle, it is better than what you can expect in the industry standard, and it's massively reducing the warm-up times. But then if you get the machine with the CSC spindle, you're basically left in, I would say, 99% of the use cases, even for current customers, you're left with no spindle warm-up times. It's turn the spindle on, start milling. And that is exceptional. And I don't see any sensor operating at that level of quality and reactivity. Now we're back at reactivity. And one thing to consider with a sensor is always, well, it's hanging inside your machine area. So you get dirt, you get the coolant going in, and all of this creates additional noise and points of failure for a sensor as well. And last but not least, while there are some spindles which have that sensor integrated, the industry standard is you stick the sensor to the side of the spindle, so you have another collision point, which in tight 5-axis movements is always a bother.
Yeah. And you just mentioned the CSC spindle, so there's also a special way Kern integrates the CSC spindle. So what you could do, so there are many CSC spindles out there. You can just connect it to your internal cooling system that might have a certain kind of quality and hysteresis, is that the right word? And what we figured out when we did that in the first place, we saw, okay, the effect is not as big as we thought it would be. So we went much deeper into that and figured out that the coolant you use inside the spindle needs to be, and this is a separate cooling circle. So if you have a CSC spindle, you will have a separate aggregate to that creates this cooling temperature. Actually, what we needed to do is to put our technology in terms of cooling and coolant management into that system to ensure that we have this marvelous 50 millikelvins that we do for the whole system to achieve the best possible outcome. And I think till today, that's what we heard. Nobody else is doing that. So we put a lot of effort into that to achieve the really best results also in terms of the CSC spindle, because if your house water, for example, that is directly connected, is moving up and down, and even we know that here, that this happens from time to time. If you run all machines at the same time, you will not get the same temperature out of your house water, then it will have effect on the most important thing actually in your machine, the spindle. And another point we learned with CSC, there's a small side effect. So if you don't have this compact shaft cooled system, and you're changing tools and tool holders, and for example, you do a roughing circle, and afterwards you go to fine machining, and the holder was in for a longer period of time, you will exchange a very warm holder to a cold holder coming out of the magazine. With the CSC spindle, also this part where the tool holder goes in, you will say the right word, so words fail me today, and vocabulary is on a low level today, but we go in and have exactly the same temperature, so you won't have any heat effects coming out of the spindle into the holder. And these are the small things we also learn as we go, and we introduce new technologies into our system that are not necessarily all developed by Kern, but we see there are useful things out there that we try to incorporate to make the machine even better.
Yes. Okay, we have one last topic to speak about in terms of the HD, and this was triggered, I think, by a video uploaded last week to our Kern Instagram, where you can see in our construction on a Friday, music is playing, and the machine gets pushed around by hand. And then and then someone commented, well, now do it to the Z-axis. And he expected, well, it's friction-free, you can push X and Y around, but Z weighs a lot, and it should actually be really hard. And, well, the surprising thing is, if you have the machine without motor currents, you can actually push the Z-axis around with 2 fingers. And the reason for this is because we have weight compensation in the Z-axis. Our approach to this is a gas piston. It has a reservoir, so energy efficiency is a little bit better, because once it compresses, the gas flow goes back into the reservoir, and it's compensated for exactly the middle of the travel. So it's overcompensating at the top and undercompensating at the bottom, but that's totally fine, because you've got the powerful motor. And what I think is interesting there is, I mean, the HD has now been on the market since 2019.
We introduced in 2019, first machines were delivered in 2020.
Yes. And what is interesting there is, since then, we haven't really introduced a facelift. And that's because it's a continuous improvement on the machine. I have actually no idea when we changed it, but the connection of that gas piston to the machine, it used to be a double degree of freedom joint, because we were like, well, maybe there's some tilt happening. And after some time, we discovered, well, no tilt is happening there, and we removed that joint. So now it's only a single degree of freedom joint there. And we actually massively improved the drag error, the follow-up error, on the Z-axis with this approach. And I think this shows that there are some parts of the machine which you haven't seen on Instagram yet, and some parts you would never consider, but there's continuous improvement going there. And I think the HD nowadays is a much better HD than when it first came onto the market.
So what I would say is that you don't necessarily see that in the performance in your specific processes, but as you said, that is what we need to continuously improve. So what we've introduced in the last 10 years is a new way of developing products, a more professional way, and of course also and not everything's working 100%, but that's what we try to achieve, of course, all the time. But nevertheless, we see as we go, for example, also in service, that things are or might create some problems, and we put energy, a lot of energy internally here to improve it, make it better, and for example to make it wear-free or to increase performance. And of course also there will be not necessarily a facelift, a little bit more than a facelift, a second generation or something like that, but all based on the experience we had over time, and also having the advantage to being very close to our customers, because just like you mentioned before, if something's not right, not only applications team shows up, but and I love to say, if you get my business card, my mobile phone number is on there, and I always have split feelings handing it out, especially if you had tough negotiations or something like that in a machine project. And you exactly know if something's wrong, they will call you. But it's a super important point. We are very close to our customers, especially also the service guys, and we know exactly if something seems to be worth looking into and improving. And I think that's one point you mentioned. That's what we figured out, and we have a dedicated group of people here just taking care about that in R&D.
We are nearly at the end of our podcast time for this week. It's still pretty early in the morning, but you probably have a whole day of meetings going on, and I have a visitor I need to get to. We ended the last two podcasts with a question, and that question, thinking back a year to when we recorded that, yes, that question was always, tell us something that happened to you that was remarkable in the past month. It can be something you learned, it can be something positive, it can be something negative.
So something remarkable that happened. Yeah. Oh, I'm not very well prepared for that question, but I will just shoot out.
I think you weren't well prepared the last two times either, which makes it even funnier.
Oh my God. So there's one thing. So right now we're planning to build a new contract manufacturing plant in Bad Kohlgrub, so very close by. So because contract manufacturing, the building is very old, and we cannot put the machines in we want, and actually it will be a huge investment for Kern, but also very important. And we see we were going into that project very with a lot of enthusiasm, and we got some pushbacks because of the fact that Garmisch-Partenkirchen here, the county, is super touristic, and it's absolutely not for industry. So we have, I think, 78% of the area is national habitat. So it's a protected environment, so where you can't build or just walk in on things like that. And so over the last 6 months, it really was a struggle to find the right spot and to convince people and whatsoever. And quite some time ago, we had a town hall meeting where the decision has to be made whether they want this specific town wants Kern to build a really big contract manufacturing there. I would say this would be the biggest building in the whole village by far, and we choose an architect from Austria, which is just doing it in wood and things like that. And after all these pushbacks and struggles we had, we got a very, very good feedback, and people are happy and welcoming us, and we're making a lot of progress. So hopefully in 2 or 3 months from now, we will have the approval to with all the plans and all that stuff, and we can buy the property and breaking ground beginning of next year. So that actually is a big relief and a big step forward for me, and something that I actually think about pretty often, which makes me happy. Yeah.
Very nice. Okay, Simon, thank you for your time. Thanks to our listeners for their time. See you next time.
Thank you, Marvin.